In this video, we're going to discuss some of the issues around spectroscopy, in particular how atoms are excited and de-excited, when we get forbidden lines, how we view the width of lines, and why spectral lines have widths. So we're going to go through all of those different things along with a couple of other pointers that help us to understand what's going on in space. So in an atom, when you have an electron and it jumps from a lower level to a higher energy level, we call that excitation. The electron is excited, it has more energy. And that can happen either radiatively or collisionally. Radiatively means that it absorbed a photon. So the right energy photon came along, the electron absorbed it and jumped up to the higher energy level. Or it can happen collisionally. You can have atoms that collide with one another, and some of that kinetic energy is transferred to the electron, which allows it to jump to a higher level. So for radiatively, we have a photon comes along, the electron on this lower level absorbs that photon, and it jumps up to a higher level. Collisionally, we have two atoms with the electron in their ground state. They collide, and in that collision, they exchange some energy, and one of them will be going slower, but one of them will have gained energy that has caused the electron to jump up into the higher level. When we have a radiative excitation, we lose photons from the source. So if we have a source of light that is continuous, there will be absorption lines. We will see an absorption spectrum. Whereas when we have things excited collisionally, we're not stealing light from any continuum source of light. We are generating light from colliding the atoms together. And so when the electrons jump back down to the ground state, they emit a photon, and so we get an emission spectrum. Now, we also have to consider de-excitation. We kind of just talked about that briefly. So this is when an electron jumps from a higher level down to a lower level. And again, it can happen radiatively or collisionally. So for radiatively, we have an electron that's in a higher level, it emits a photon, and the electron jumps down to the lower level. And in this case, we're going to get an emission spectrum. So we have something that is giving us the electrons in a higher level, and then they jump down, we get emission. When we have collisional de-excitation, we've got an excited electron here, and through the collision, it loses energy, but it doesn't need to lose a photon. The energy is given away as kinetic energy into the collision. And so what happens here is that we don't see anything. And that's important for some things that happen, especially in space. Let's talk about forbidden lines. Most transitions, most electron jumps happen spontaneously. They happen very quickly. The time that an electron spends in a higher energy level is of the order of nanoseconds, maybe 10 nanoseconds. And so it jumps down pretty quickly. But there are some transitions, and we have to get into quantum mechanics to understand why, but there are some transitions that happen much more slowly. They can last seconds or even longer. These transitions, that is the electron jump from a place where the lifetime in that state is long, that electron jump is unlikely to happen. You're more likely in a gas to have a collision that de-excites the electron. So you don't have time to have it emit a photon, and so we call them forbidden lines. It's not that they can't happen at all, it's just that they're extremely unlikely in terrestrial environments. So what we get is, the electrons might be in upper levels, but they don't get to emit anything because they de-excite by collision with other atoms. When we see forbidden lines, it tells us we must have a very low density gas because we have enough time between the collisions of the particles that it is de-exciting by a photon and not by a collision. The idea of forbidden lines was something that came out of quantum mechanics, but then was able to be tested with astronomy where we have these low densities. In this picture of the Helix Nebula, the red here and then the yellow is actually where there's a mixture of red and green. The red and the green, they are forbidden lines that we cannot see in our labs, but now we can see them in space. talk a little bit about the details of spectral lines. When we have an emission line, we've got something that a whole bunch of atoms are then having the electrons jump from one energy level to another and giving us a photon. The number of photons emitted are what gives us how bright that line is. And so what you get is an emission line. Likewise, if you have something that's absorbing the light, so we've got some atoms and the electrons are absorbing photons and jumping up, the amount of light missing depends on the number of photons absorbed. So how many photons can the gas absorb as the electrons jump up? And so what we see here is we've got intensity versus wavelength, and we've got how many photons were used. And this is basically you're adding up all the photons. That's the area under the curve. And here we've got one where we start at the level of light that we would have before it passed through our gas, and then we can see how many photons are missing. And again, that is the area underneath the continuum level. Notice that these are kind of Gaussian shaped. They may be Gaussian, they may be not quite, but they are definitely never infinitely sharp. And we're going to get into that shortly. So when I say they're not infinitely sharp, they have this shape here. This is basically a Gaussian. And we tend to define the width of the line by the full width half maximum. So the area under the curve gives us the total amount of photons, but the width is also giving us some information. And so we call this the full width half maximum. You go to half the maximum height of the curve and you halve that, and at half, how wide is it? There are lots of reasons why the widths of lines are not infinitely thin. So let's talk about spectral line broadening. We're going to start with what's called natural line broadening. And this has to do with quantum mechanics. Heisenberg's uncertainty principle tells us that we cannot know an energy state more accurately than this equation. It's basically delta E times delta T equals h bar, Planck's constant. And so we're here, the delta T is the lifetime of the state. Okay, and so what that means is that because we don't know how the energy of an energy level to perfect accuracy, we don't actually know what the transition is. When we're looking at spectral line, we're looking at the difference between one energy level and another. But except for the ground state, all of the energy levels have uncertainty in them. So that gives rise to a natural broadening that is to do with how much uncertainty there is in the energies. I just said the energy may not be stated to better than this. And again, this delta E is the uncertainty in the energy. It's not the same delta E as like when you have an electron that jumps from one energy level to another, and that's a difference in energy. It's not that. This is the uncertainty in the energy of the two energy levels. The typical lifetimes of most things that we think of as being, spontaneous in their de-excitation is about 10 nanoseconds and gives a natural line width of about 10 to the minus 5 nanometers. That's nice and small. Remember that visible light is in the 500 nanometer-ish range. So it's a very small broadening, but it is there. Now, there are other ways that lines get broadened that have a much bigger effect than the natural line broadening. The most obvious one is the thermal Doppler broadening. This depends on the temperature in the gas. When we have a gas at temperature T, then the particles are moving with a velocity that's determined by that temperature. So here you can see a Maxwellian distribution. And what you've got is a most probable speed. In here, that's marked as 1. That's the peak. But that's different from the RMS speed. The most probable speed is given by this equation here. It's V probable is the square root of 2kT over m, where K is the Boltzmann constant, T is the temperature, and m is the mass of the particles. So if it's hydrogen, it's just the mass of a hydrogen. You can see that the RMS speed is a little higher, and the equation is given here, and that's because the curve is not symmetric. So if we take the root mean square of to find the average speed, it's a little higher. But we want to use the most probable speed in order to get the distribution of speeds. So let's think about what's going on. You're looking at a gas and the particles are moving in all directions. The most probable speed is given by this 2kT over m square rooted, but it's actually moving in lots of speeds, higher and lower than that. and the particles are moving in all directions. And so we get some that are going to be blue shifted. If the gas particles are moving towards us, then any line from it will be blue shifted. And the particles moving away from us, any line will be red shifted. So here you can see these lines are moving vaguely towards the observer, these are moving away, whereas these ones that are kind of moving transverse across the line of sight do not get affected. So we get a full distribution of red and blue shift according to the most probable speed, but also the other speeds that the particles are moving at. And the line will be equally broadened both to the long wavelength side and the short wavelength side. And it's broadened by the Doppler equation. So here you can see, depending on how fast the atoms are going, we get a broadening that's given by the ratio of that speed to the speed of light, and it depends on the wavelength. But what we'll get is something that is blue shifted and red shifted, and it gives us a width. And we're going to have a look at what sort of typical numbers those widths can be in a second. Now, this is really important because now we know this, we can use this to determine how fast things are moving in space. Remember that there is an m in this equation. And so for a given temperature, the more massive particles are moving slower. So you're going to have skinnier lines, sharper lines for heavier elements than lighter elements. And that helps you determine whether you're really seeing a Doppler effect and to double check your speeds that you get out of it. So let's do a quick example. Here we have the most probable speed. And so at 6,000 Kelvin, which is a little hotter than the sun, let's work out how much the motion of the hydrogen atoms affects the Balmer alpha line. That's the 656 nanometer red line in visible light. Remember, this is the Boltzmann constant, and this is the mass of hydrogen. Those are over here. If we put in the numbers, we find that the most probable speed of our atoms is of the order of 10 kilometers per second. And so now we can plug this in and say, you know, the change in lambda compared to lambda is given by V over C, which gives us a relative change of 3 times 10 to the 5 for the ratio of the change in lambda to lambda. So if we put in the red line color, the 656 nanometers, and we multiply it by this term, we find that we have a 0.02 nanometer shift. And remember, it has to go to the blue and the red. So the full width of the line is going to be 0.04 nanometers. And you can see that, you know, that's a small number compared to the wavelength. So it should look fairly sharp depending on our resolution of our instruments. There are some other broadening mechanisms. The one that is most commonly used in astronomy is the collisional or pressure broadening. In this case, we've got a line width, and you can see here in this figure, we have, this is actually looking at something in a gas phase, but what we've got is, as the pressure goes up, this line gets wider and wider. And the line width is given by this alpha L. And alpha L is then related to both the pressure and the temperature. In this case, the alpha O is some sort of anchor point. You can think of this as being, we've determined at a pressure and temperature of T0 and P0 what the width is. And so now we can get the relative width at any pressure temperature. Now, remember that what's happening is you're having lots of collisions. And so although while temperature dictates the speed, you also have how dense the gas is affects how many collisions you have. So it affects the distribution of speeds. And so you can get more collisions. The velocity is also going to depend on the nature of the particles themselves. So that n value for what the dependence on T is actually depends on how your particles collide. You can think of it as being, when they collide, what's the exchange of kinetic energy? For collisional broadening, we use this in stars. We can see that smaller stars are more dense, they have higher pressures at the atmosphere, and so they have fatter lines in their spectra, and this allows us to use the spectrum as a diagnostic of how big stars are. So there are a couple of other broadening mechanisms. One of the most useful is the Zeeman effect. This is basically when you have a magnetic field. If you have a magnetic field, the energy levels get split. So instead of having just one energy level that the electron can go to, it has 3 very close together. And so now when you have transitions from the ground state up to what is originally just the first excited state, there are 3 options very similar in energy. And so what you see looks something like this. And you can see here, there's not a magnetic field here. It looks like it's a single line. Then we have a magnetic field and it splits. But this only works if you've got high resolution or a strong magnetic field. For a weaker magnetic field or low resolution, you're going to get something that looks like this, where it just looks like it's all stuck together. And so you really see a broader line, and that is down to an unresolved magnetic effect. There are also some other things that we get for unresolved stars. That is to say, when we're looking out at stars, we can't necessarily see the edges of the star. We just see it as a point of light. Anything that's happening on the surface of the star may give rise to Doppler effects in the emission lines. If it has an expanding atmosphere, that's also going to have an effect on the Doppler effect. And if it's rotating, one side's moving towards you, one side's moving away from you, that could also add to the Doppler effect. So the same sort of effect as we saw for the thermal Doppler effect, but now it's not due to the temperature of the gas, it's due to other motions. Okay. Briefly, when we talk about spectral line intensities, I mentioned this earlier, that the line strength is proportional to the area of the line. And there's a term that we use in astronomy that's called equivalent width. So here I've got an absorption. Here's the continuum. Here's how the absorption looks. We've got a whole bunch of light missing. If we were to have this as a just straight thing, this has the same area as this line profile. And so we consider this to be the strength of that absorption. If it was going to be just straight down and removing all the light, how wide would this be? And so that is called equivalent width. Now, if this gets all the way down to the bottom, that is to say we end up with no light here at all, then that is called saturation, and we wouldn't be able to tell how much light is missing. We'd only be able to put a lower limit on how many photons were absorbed. So let's talk about Boltzmann's equation. This is something that's really useful for us to understand and how we apply that equivalent width that we were just looking at. So what we've got, a number of atoms in a given excited state. When they jump down, it gives us an emission line. Causing them to jump up to that excited state gives them an absorption line. But either way, the equivalent width is a measure of the number of atoms in that state. So we've got this excited state. The excitation can happen both collisionally and radiatively. The de-excitation can happen both ways. And in fact, in all gases, it's going to be happening both ways. And both of them depend on T. Remember that collisionally, that means the kinetic energy is related to the temperature. But also, if we want the photons are related to temperature as well. How many photons we have depends on whether you've got a radiative source that's a black body, that would be temperature dependent, but it also depends on how many atoms are de-exciting. The number of photons is going to increase rapidly with temperature. That is to say, as you go up in temperature, you're now exciting more atoms, and so you're going to have more transitions down, and you're going to have more photons. And so even though you can also have more collisions, you're going to have a lot more photons generated. We can get a measure of how this all fits together. At equilibrium, that means is that it's in a steady state. The number of excitations equals the number of de-excitations. It's not that it's not doing anything. Gas atoms have electrons that are constantly being excited and de-excited, both collisionally and radiatively, but the number of them is constant. And then from statistical mechanics, we can state that the number of atoms in state A is related to the number of atoms in state B. And so what we've got here is this is the number density of atoms in state A compared to the number of density of atoms in state B. These are statistical weights for those two states, and these are the energies. When we're looking at our equivalent widths, we can actually use it to apply an equation like this and start to understand how many atoms we've got by looking at the amount of energy we have in the two states. Boltzmann's equation works well for neutral atoms. So you've got electrons like in a hydrogen atom, and it's jumping from 3 to 2 or 2 to 1 or 1 to 4, but it's staying neutral, the electron stays attached. As we increase the temperature, we go from a neutral gas to something that is partially ionized, something that's totally ionized. Once it is a hot gas, it's going to contain neutral atoms and ions and free electrons. And the hotter it gets, the more electrons you have. The more electrons you have, the more chances you have of recombining, and so the more chance you have of having more neutral atoms. And so you have this combination of, as you get hotter, you still have neutral atoms, but you also have more free electrons, and so that affects what you're going to see in that gas. And so what we're seeing is a constant balance between neutral atoms and ionized atoms with the electrons missing. And so Saha, an Indian astrophysicist, came up with an equation that was basically similar to the equation that Boltzmann had, but now it's looking at densities of the ions in adjacent states. So here I've got the number density of ions that have just lost one electron, and here I've got the number density of neutral atoms. A is a constant, T is still temperature, and then this is the number of electrons. This is the ionization potential, because that's how much energy it takes to knock the electrons off the atoms. And here we have temperature again. And so this actually works for any two adjacent ionization states. So it could be 2 plus and 1 plus, or 3 plus and 2 plus. But what this allows you to do, since we can actually trace both ions and neutral atoms in the gas phase from their emission lines, we can then start to understand the relationship between the neutral gas, the ionized gas, and the electrons to understand the state of, say, a planetary nebula. So in this video, we've talked about excitation and de-excitation, about how line broadening happens, about how we measure the lines in equivalent widths, and then how to use the strengths of lines to diagnose what's going on in objects in space.